Okay, so we have Rn. We're using same notation. So we have x sub 1, x sub 2, x sub n. Oops. Da, 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 da. By the way, if I make a mistake, please tell me immediately because I made a lot of mistakes yesterday. 4 entries. And then I cannot fix that.
Yeah,
so
not that much. No worries. Yeah.
Okay. So this is n dimension. In matrix, we are using the n entries, right? Okay. Means the real number in here, real number. And real number symbol. Okay, so we have, this is just index, and we have, this symbol is belong to, right? It's in, is in, belongs to. So x sub j is belong to the real number. Okay, now we have a 0 called the origin, right? Okay, so we have R1, one dimension, right? So we have just order pair 1, right? Order pair 1, just one single element there. So x sub 1 is in R, and R2, 2 dimension. So x sub 1 order pair, xj in R, j is in 1, 2. Okay, R3, 3 dimension, right? So we have triple pairs, x sub 1, x sub 2, x sub 3. And x sub j is in R, real numbers. And j equal to 1, 2, 3, right? So calculus 3 and linear algebra, we talk about the more than 3 dimension, right? So calculus 3, they talk about x, y, z, right? Over x, y, z. And there's more than 3, then x, y, z, w, right? And then ran out the letters. So we are using x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, right? And so on. Okay, now definition. Position vector. So let P equal to P sub 1, P sub n be the coordinate of a point in Rn n vectors, I mean n dimension, then they're using P. Then the vector. They're using 0p. It's like this, like we are using like AB, right? AB, like that. Then this is a starting point and end point, right? Start and point. So they have a 0, this is a 0, and P means that start is 0 and end is P. So they're using tail tip with, it's a tail at 0 and its tip at P is called position vector of the point P. So we write 0p. This is not O, this is 0p. And this is P1 until P7. Okay. Let me using so 3-dimension, X, Y, Z, right? So this is X, right? This is Y, this is Z, right? Okay, then we have start 0, and we have a point. So call P. So they have 0p, which is, we have P1, P2, P3 in that case. Okay. So we said a tail at 0, the start point and end point is P, right? Okay, now some of you took calculus 3 with me, so you guys know the position vector from P to Q. So let me write down position vector from P. So by the way, this is a vector notation, right? So we are using this vector notation. In the textbook, it's a bold, then there is a vector notation, right? Like this, also vector notation. Okay. P to Q, also vector from P to Q. So PQ, then Q minus P1, Q1 minus P1, and Q2 minus P2, Qn minus Pn, right? This one we can use this way, right? P. Q2, P2, Pn. So this is come from 0Q minus 0P. Yeah. Okay. So we talk about if we have OP, then we can say that there's AB. We have AB. So we say that this is AB. So OP note. Zero P, they should give to all. And AB has same length. So we have a fancy vocabulary, which is magnitude. Length means magnitude and same direction. So basically vector has the magnitude and direction. So we call it vector. So let me write down the definition. Vectors. Vectors in Rn. Okay, let Rn equal to x sub 1, x sub n, x sub j is in R for j equal to 1, 2, until n. Then vector x equal to component x sub 1, x sub 2 until x sub n is called a vector. Vectors has both sides, means the magnitude, which is the length, and direction. So we called the numbers in here, we call the component. X sub j are called component. Over x. Okay, highlight vocabulary. Vector. Vector has the same size and direction and component. Okay. Let's talk about linear combination, yes? So let's talk about linear combination. Then we're done. Very interesting. 4.1. What else do we have? Okay, so we have this form, right? So we have u equal to u equal to u sub 1, u sub 2, u sub 3. And then we have I, which is 1, 0, 0. We have J, which is 0, 1, 0. We have K, which is 0, 0, 1. Okay. We say that U is a linear combination. We talk about this as a third time, right? So linear combination. So we are going to talk about more combination terminology of these vectors. Why? Because we can express this one like this. So since we can read them, u equal to u sub 1, I equal to u sub 2, oops, u sub 2, J, thank you, plus u sub 3, K. All right, because I equal to 1, 0, 0. If we multiply add them, we get u, right? That's why. So we call the u is a linear combination of these vectors because the form is like that. Okay? Ooh. So let's remember the form. Okay, it is very short. Let's talk about 4.2, vector algebra. So addition, definition, addition of vectors in Rn. Okay, so we have, if we have vector u, which is u1, u2 until un, column vector, right? And v equal to v1, v2 until vn. It's in Rn, n dimension, right? So we have n element. Okay. Then also addition, u plus v also in Rn, and it's defined by u plus v equal to u sub 1, u sub 2, u sub n plus v sub 1, v sub 2, v sub n. We add it together, right? U sub 1 plus V sub 1. U sub 2 plus V sub 2. U sub n plus V sub n. Okay. We have a properties of a vector addition. Theorem 4.2.1 properties of vector addition. Okay, so commutative law, associative law, narrow law, and additive identity. U plus V equal to V plus U, commutative, right? And we have associative. So this one, same as that one, right? And additive identity, which is 0. So we added 0, we get the original one back. So additive identity and additive inverse. So we have minus U, we get 0 vector, right? So we call additive inverse. All right, so we have a scalar multiplication. Definition. Scalar multiplication of vectors in Rn. Okay, so the vector is in Rn and k is in real number, scalar. Then scalar k, U is in Rn, is defined by Ku equal to K. U is Rn. We can make one U1 until Un, right? Okay. Equal to, we said that K U1 and K UN. Okay. More properties. Ooh. Theorem 4.2.2 properties. Yes, properties. But it's understandable, right? Not hard theorem. Yes. Associative, commutative, and scalar, everything you guys know that. Multiplication. Okay. Ooh. Ready? U is a vector, V is a vector. And K is a scalar, P is a scalars. All right. So we have a distributive law. Distribute, then we get Ku plus Kv And we have a scalar distributive, so k plus p, u, distribute. So ku plus pu, right? Associative k, pu, then we can kpu, we can do that associative with a multiplication, right? Okay, number 4. Multiplication identity, right? So 1 times u, we get the u back, right? Number 4, 5. Yeah. So everything is understandable, right? So I don't have to prove. Yeah, we don't have a number 5. Yes, okay. Linear combination again. Oh, linear combination again. Definition about the linear combination. So this is the 4th time we are using it, linear combination. So definition. Linear combination. A vector V is said to be a linear combination. So we remember from the maybe 10 minutes ago of the vectors U1. They changed that. It was U earlier, right? Okay, U1, U2, U7. If there exist scalars A sub 1, A sub 2, A sub n, such that, yeah, we have this form, right? So since they're using V as a linear combination, we express this way. V, and then the scalar is A sub 1, vector is U sub 1, so A sub 2, U sub 2, plus A sub n, U sub n, right? Okay, so we had example before, so this is example. Maybe highlight the first linear combination. V is a linear combination, then we have to have this form, right? Yeah. So they're using different letters, variable, but it's the same form, right? Okay, linear combination is like that. Okay, let me show you this example so we understand what kind of form is this, right? So we have scalar first, 3, and we have a -4, 1, 0, and plus 2, we have a -3, 0, 1. All right, then we have properties earlier, so we can distribute, right? So we get, what do you get? Thank you very much. -12, right? And 3, 0. We have -6, 0, 2. Okay, now we add them by vector addition, right? So we have -12 plus -6 and 3 plus 0 and 0 plus 2. So we get -18, +3, 2. Excellent, right? Okay, so this is a process we're doing that, but as a linear combination, we have 3. So summarize 3 dot -4, 1, 0 plus 2 -3, 0, 1, which is -18, 3, 2. Very good. So thank you, Alan, the chat. So we get, this will be constant and vector u plus the scalar. Yeah, I should say scalar and vector u2, right? And then vector v. So we say that v is a linear combination of these vectors, right? Okay. So I'm not gonna write down because we have a definition here. All right. We done. Wow. Okay. 4.3 geometric meaning of the vector addition. Okay, very short, right? So geometric vector addition, we have a definition. So following the definition all the time. G of vector addition. Okay, so we have 2 vectors. Let me write down. Let me just show this one, right? So u this is a vector u, and then there is a vector v. Okay, then they say the tail of u to the point of v. So they have a tail and tip earlier, right? So tail means from the starting point, right? Well, let me write down tail. End point. They're using tip earlier, right? Then we will get that is u addition of vector u and v. That we are using the arrow here too as well. So this is a u and v. Okay. they have a different one. So how about this? This is U. And they start to U, then from the tip, they start to V, right? Okay, so V will be here. Okay, so same concept. So from the tail, starting point, end point, we connect. And this is U plus V, right? Okay, now we might use diagonal, right? So if we have U, if we have a V, this is a U, this is a V. Okay, let us draw the parallelogram. Yeah, looks like, no? Better? Okay, so we are drawing diagonally, right? So we say that this is a U plus V. Okay. Okay, how about subtraction, huh? So we have subtraction. Yeah, so subtraction. U minus V. Okay, so if we have U here, if we have a V here, that's the V, right? Okay. Let me write down. This is V. Yeah, we knew that from the tail connect, that's U plus V, right? Upload. So this will be U plus V, right? Okay, now, look, if we make an opposite direction from the V, since the V from the tail to tip and the point is here, so we have to using same length and opposite, right? That's the negative V, right? Okay, so we will have, then we are using same direction with the same length. that is the same vector, right? So let me draw V here, I mean U here. Okay, so it's U. Then V, I want to make a negative opposite direction. So that is a little bit longer. Huh? Okay, so there is a negative V, right? Okay, so we add them from the tail. So there will be green. There will be U plus negative V, right? Okay. Because this is U minus V, same as vector U plus negative V, right? Okay. So I think we can stop here. Thank you for coming. You have a nice evening.
All right, thank you.
Thank you. Bye.